Hello, today we'll be doing a 2010 AP Physics C free response, the third one. The long straight wire illustrated above carries a current I to the right. The current varies with time t according to the equation I equals I initial minus kt, where I initial and k are positive constants, and I remains positive throughout the time period of interest. The bottom of a rectangular loop of wire of width b and height A is located a distance d above the long wire, with the long wire in the plane of the loop as shown. A light bulb with resistance R is connected in the loop. Express all algebraic answers in terms of the given quantities and fundamental constants. Part A asks us to indicate the direction of the current in the loop. So we're looking for the current going through this section. And we know that the equation is I equals I initial minus kt, and that I and k are positive, meaning over time this current is decreasing. So we know that the current in the wire is decreasing. Now if you use the right hand rule, you point your thumb in the direction of the current and you curl to find the direction of the magnetic field. You see that there's a magnetic field coming out here. So a magnetic field out of the page. But since the current in the wire is decreasing, the square is going to come up with an induced current to counteract it. So because the current is decreasing and there's going to be an induced current to counteract it, the current through this is going to be counterclockwise. It's just because the flux is decreasing. For part B, we have to indicate whether the light bulb gets brighter, gets dimmer, or stays the same brightness over the time period of interest. So during this time period, you realize that the field and the flux, once again because of this equation, they vary linearly with time. So the field and flux vary linearly with time. And then the mth is the derivative of the flux. So mth must be constant. And when the mth is constant, R is also constant, the resistance of the light bulb. And the brightness is based on the power. Basically, we can just go to the power formula, which is P equals mth squared divided by R. And because mth is constant and R is constant, the power is constant and the brightness will remain the same. Part C asks, determine the magnetic field at time t equals 0 due to the current in the long wire at distance R from the long wire. For that, we can go to this formula. And the magnetic field is times the derivative of the length is going to be equal to this constant, which is 4 pi times 10 to the negative 7 newtons divided by meters. And that is going to be equal to mu, which is just a constant, and I is the current. So here we are looking for the magnetic field. The length is simply 2 pi R equals mu I, and this is at time equal to 0. So when t is equal to 0, I is simply going to be I initial, this fundamental constant, divided by 2 pi R. And that is what B is equal to. Moving on to part D. Derive an expression for the magnetic flux through the loop as a function of time. So the formula for magnetic flux is equal to the integral of B dl. In this case, it's going to be mu I over 2 pi R times dA, which we found in part C. And we can replace dA with dr in this case. And now we just have to add our limits of integration. So if you look at the image, we have a distance of A, well, actually a distance of D going up to A plus D, because we're integrating along this length. B is going to remain constant, it's only this distance that's going to change. So the distance goes from D to A plus D. You can pull all of this out because it's a constant. We have mu I over 2 pi r, and then we take the derivative of dr times, well, over r. And that's here. And then through the integration rules, we know that that is mu. In this case, I is going to be is kt divided by 2 pi times the ln of a plus d over d, simply because those were our endpoints. And yeah, that's about it for this part. Part E, finally, it says derive an expression for the power dissipated by the light bulb. So power is equal to m squared over r. And m is equal to d theta dt. So m is going to be d dt over the flux. And we found the flux in part D, so that's simply mu I minus kt times 2 pi ln of a plus d over d. And if we carry out the derivative, we get negative b 2 pi ln of d plus a over a. And then we ddt this part. All of the things we took out were constants. And when we do that, we get simply negative k, because I minus kt, when you take the derivative of it, that's a constant, and that t is going to go away. And so this is the answer you get. So let's just set that equal to g to keep it simple. And that was m, so we just have g squared divided by r. P equals that. And then you could just plug that in for g, and you'll have your answer. And that's it.